Inflection points. So remember, earlier in the term, we learned about something called inflection points. An inflection point is a point on the graph where a function f of x changes concavity, which means to the left of an inflection point, the concavity is going to be different than what's to the right of the inflection point. So how do we locate inflection points and how do we solve for these mathematically? So let's assume that we have the original function and we can look at a picture. If we have a graph like we see below, we can identify the inflection points by looking for the value of x where our function changes concavity. So here we see that x equals 1, we're going to have an inflection point because to the left we're concave up and to the right we're concave down. So if we have a picture, we can look for where concavity changes visually by looking at the bend of the graph. We can also use the first and second derivative to talk about where we'll have inflections of the original function. Let's talk about how that works. If f prime of x has a horizontal tangent line at q, and the first derivative changes from increasing to decreasing or decreasing to increasing, then q is an inflection point. Let's talk about why. So remember, when we talk about the first derivative, we can use the first derivative to talk about the second derivative. So at the places that we have horizontal tangent lines of the first derivative, that's where the second derivative equals 0. Now, that's one of the things we look for when we're looking for inflection points. But what we also need is for the concavity to change. So if the first derivative is increasing, the second derivative is positive, which means that the original function is concave up. If it's then decreasing, the second derivative is negative, and the original function is concave down. So since increasing and decreasing on the first derivative relate to the concavity of the original function through the sign of the second derivative, that means that whenever our first derivative changes from increasing to decreasing or decreasing to increasing, then we're going to have an inflection point on the original function. And we know that we change at the places where we have the horizontal tangent line. Now, if we have information about the second derivative, then we need to know where the second derivative changes signs. So if the second derivative changes from positive to negative or negative to positive around a point, then that point is an inflection point because the sign of the second derivative tells us the concavity of the original function. And so if the sign changes, that means that the concavity changed. And again, that's our definition of inflection point, the point where the concavity changes on the original function. So let's look at a couple of examples of how we might calculate where an inflection point could be on a function. Example 1. Suppose f of x equals 2x cubed minus 3x squared minus 36x plus 14. Find all the inflection points of this function. So we could graph the original function and look for where it changed concavity. We could examine the first derivative for increasing and decreasing, but I'm going to use algebra through the second derivative to try to determine where the second derivative changes signs. So to get to the second derivative, I need to go through the first derivative. The first derivative here is going to be 6x squared minus 6x minus 36. So my second derivative here is going to be 12x minus 6. So remember when we talked about critical points. Critical points divided up our interval where our function existed, and within each little interval, the sign was always the same. The same thing is going to happen with the second derivative. So that means if I find out where the second derivative equals 0, that's going to tell me how I can divide up my number line for the original function to examine the sign of the second derivative. So here, if I solve for x, I'm going to get x equals 1/2. So that means if I were to draw a number line to represent the sign of the second derivative at every possible value, that what I need to examine is what's happening from negative infinity to 1/2 and from 1/2 to positive infinity. Those are the two places where I could have different signs. So to the left of half and to the right of half. So I want to pick something a little to the left of half to test here. So I'm going to pick 0. If I plug a 0 into the second derivative to get the sign, I'm going to get -6. So to the left of half, x equals half, my second derivative is negative, which tells me that my original function is concave down to the left of 1/2. When I test something to the right of half, I'm going to pick 1. Again, I can pick any number I want that's to the right, but I'm going to pick something that makes my life a little bit easy. So if I plug a 1 into the second derivative, I get +6. So since it's positive, every single value to the right of 1/2 would give me a positive second derivative. So to the right of 1/2, the original function is going to be concave up. So here, I have switched from concave down to concave up right at x equals 1/2. So that means that x equals 1/2 is indeed an inflection point. Let's try another example. Suppose that we have the function 3x to the 4th minus 4x cubed plus 6. We want to find all the inflection points of this function. So again, I'm going to begin by finding the second derivative. So my first derivative here is going to be 12x cubed minus 12x squared. The derivative of 6 is 0 because 6 is a constant. My second derivative here is going to give me 36x squared minus 24x. Now, again, I want to determine when this equals 0 so that I can figure out how to divide up my interval to look for the various signs of the second derivative. So if I factor out a 12x, I'm left with 3x minus 2. And again, I want to know when that equals 0. So I set each term equal to 0. If I set 12x equal to 0, I get my first possible inflection point, which is x equals 0. And if I set 3x minus 2 equal to 0, I get x equals 2/3. So what that tells me is that the intervals that I need to consider for where my sign is possibly going to change is from -infinity to 0, from 0 to 2/3, and from 2/3 to positive infinity. So I want to test out some numbers to see what the sign of each of these intervals is going to be. So I start by testing something a little bit to the left of 0. So again, I'm going to plug that into my second derivative. So if I plug -1 into my second derivative, I get +60. And so again, I'm interested in whether it's positive or negative, but here I know that all values less than 0 are going to give me a positive second derivative. I also want to test something between 0 and 2/3. So I'm going to plug in 1/2. So if I plug half into my function, I'm going to get -3. So that tells me that all the values between 0 and 2/3 are going to give me a negative second derivative. Finally, I want to test something a little bit bigger than 2/3. So I'm going to test +1. So if I plug a +1 into my second derivative, I'm going to get +12. So I can see that my concavity is changing from concave up to concave down to concave up. So that means that both 0 and 2/3 are both inflection points. Let's look at another example. Example 3. Find all local maximum, minimum, and inflection points for 2x cubed plus 3x squared minus 180x plus 5. Oftentimes, maximums, minimums, and inflection points are all grouped together because when we're finding first and second derivatives, we can use all of them simultaneously to find out different information. So let's take a look at this. So let's start by finding the first derivative here. The first derivative will help us find the critical points, which we need to identify local maximums and minimums. So the first derivative here is 6x squared plus 6x minus 180. I want to know when the first derivative equals 0. I'm going to factor out a 6 here to try to make my work a little bit easier to factor. And I want to set that equal to 0. So I can factor this down into x plus 6 times x minus 5. So now I have 3 things multiplied together equals 0. That means one of them has to be 0. So we know that 6 doesn't ever equal 0. So I have 2 critical points here. I have x equals negative 6, which will make the first parenthesis 0, and x equals 5, which will make the second parenthesis 0. So I have 2 critical points, and I want to know whether they're going to give me local maximums, minimums, or neither. But since I also want to find inflection points, I can use the second derivative for all of that. So my second derivative of this function, I'm going to go back to the unfactored form, is 12x plus 6. So let's start by looking for inflection points. So again, I want to know where this equals 0, so I know how to divide up my number line. If I subtract 6 over and divide by 12, I get x equals negative 1/2. So negative 1/2 is the dividing point where it's possible that my second derivative changes signs. So again, I want to test something to the left, and I want to test something to the right. If I plug in something to the left, I can test negative 1. If I plug negative 1 into the second derivative, I get 12 times negative 1 plus 6 gives me negative 6. So to the left of negative 1/2, my second derivative is negative. So that means that I'm going to be concave down. I also want to test something to the right of negative 1/2. So if I test something to the right, I'm going to use 0. If I plug in a 0 into my second derivative, I'm going to get positive 6. So that means to the right of negative 1/2, I'm concave up. Since I changed concavity, that means that negative 1/2 is an inflection point. So x equals negative 1/2 is an inflection point. I'm going to put IP for inflection point. Now, I also need to classify my critical points. So notice that one of my critical points is to the left of negative 1/2, and one of my critical points is to the right of negative 1/2. So since I know the concavity to the left and right, that will also tell me if my critical points are going to be local maximums or minimums. I can also plug them directly in, but it'll give me the same result. So negative 6 is going to fall to the left of negative 1/2. So that means that it's going to be in the portion of the original function, which is concave down. Remember, we were negative to the left of negative 1/2. If your function's concave down, that means your critical point is a local maximum. Similarly, x equals 5 is to the right of negative 1/2, which means it's in the part of the function that's concave up, because the second derivative is positive for everything to the right of negative 1/2. If we're concave up and you have a critical point, that means your critical point has to be a local minimum. I could have also plugged negative 6 and 5 into the second derivative to get the sign if I wanted to be doubly sure, but it's good enough to already know from before, from our intervals here, what the sign of the second derivative is going to be everywhere to the left and right of negative 1/2. So I know now that I have a local max at negative 6, a local min at 5, and an inflection point at negative 1/2. Let's look at some more problems.